but thank you. All right, so I just want to start off. I think Yuri gave me a good introduction. I'm not that famous, actually. But yeah, my area of research is distributed systems, operating systems, and networking. I love those things. I believe they can make the world a better place, and it's very interesting, and it solves a lot of problems. Unfortunately, as we've seen, there's also some problems that come with the internet and connectivity and connecting everyone together. So there's things to work on as well in that area. Today, I'm going to focus on distributed systems and how we start building them. So, yeah, so it's interesting to see the languages you have. I have a couple of charts or a couple of survey questions just to get a feel for who you are. I'll be in Kyiv next week, so hopefully I can meet some of you in person. But in the meantime, let's just jump in and get some introductions ahead of time. I should mention, I got my PhD from University of Santa Cruz. Well, actually, University of California, Santa Cruz, in secure distributed storage. And I'm a professor at San Jose State University. However, I don't use titles. I usually just ask my students to call me Ben. So I'm happy if you just call me Ben. If you prefer Dr. Reed or Professor Reed, that's fine too, but I prefer Ben. Okay, so this is cool. It's interesting to see how broad and uniform the languages you're comfortable with. I love Python. I love writing in Python. It's very fun. It's so slow though. It's so slow. So I think most of the work I do is in Java. I love C for its simplicity. I use C in the operating systems class. And I also like C++, although I'm not as good at the latest C++, starting at 17. Actually, starting C++ 11. I didn't stay up to date with it as much as I wanted to. And I'm trying to learn Rust. Rust is the language I'm working on right now. So, all right, so let's go to the next question. Let's see if I can make this move. Here we go. Whoops, this is not right. Oh, sorry, let me skip this. Here we go. Yes. All right, so the next question. And again, this is just to kind of see where you are. What is your favorite IDE? So your favorite integrated development environment, okay? So that can be Vim, yeah, great. Actually, the two I was gonna point out are already there. So that can be Vim, that can be VS Code, or, oh, anything from JetBrains, yeah, I'm totally with you there. Yeah, I was always a VI user, and then I tried to switch to Emacs because that's what all the smart people were doing, was using Emacs. I never really got comfortable at Emacs. And then I started using Eclipse, and Eclipse was awesome. I actually worked on Eclipse for a little bit when I was at IBM. And then I found IntelliJ. So awesome. So I love IntelliJ. And I use IntelliJ, C-Line, and Python. Those are my favorite IDEs. Oh, and I use Android Studio, all of which are basically IntelliJ. Okay, but the cool kids, I recognize this. The cool kids use VS Code. So yeah, okay, awesome. And it looks like you have a lot of cool kids at your school. Good. Okay, so I have another question for you. Yeah, have you used Spring Boot? Or do you know what it is? I guess this is more for Java people. Spring Boot is a Java framework. I started using Spring Boot about 2 years ago. I'd heard of it before, but it's kind of cool. It's pretty magical. It uses annotations, kind of like Python does a lot, to allow you to build servers, network servers, very quickly and nicely. Cool. Okay. Thank you. And let's just do. Okay, this is just to kind of see where your knowledge is. It's not a grade. I just want to kind of get a feel for where everybody is. Okay, in terms of their understanding of the concepts I'm going to talk about today. So, what port does HTTPS usually run on? So when you type HTTPS : / host name, what port is your browser usually connecting to? Okay. All right. Good. All right. So I'm curious. Just so here 443 is the correct answer. Does anyone know what port 53 is used for? 53 is an important port. Does anyone know?
Docker, maybe? Docker?
Docker? No, I mean, kind of. Everything kind of, yeah, DNS. Yeah, so Docker uses DNS, right? So, but yeah, so DNS servers run on port 53. Does anybody know what port 25 is? Or what it used to be? We don't really use port 25 anymore. But what was port 25?
SMTP, I think.
Yeah, SMTP.
Email.
Right, for email. Very good, very good. Yeah, and port 80 is the unencrypted HTTP port. Okay, awesome. So one more one more exam, and this is just a question. This is just to understand where you are. So if we have the 32-bit integer, which is in hex 0x BADBEEF. So this is the hexadecimal number. We take this hexadecimal number and we store it in memory. So when we store it in memory, it's going to use 4 bytes. So we store those 4 bytes at this address, 1 bad 2. Okay, so we store those 4 bytes starting at that address. So since there's 4 bytes and that address points to 1 byte, what will be the first byte we store? What number will it contain? Okay. So again, I'm not really looking for the right answer. I'm just trying to understand conceptually where you all are at. Okay. So you can just guess if you don't know. All right. Okay. Good. All right. So there's actually 2 answers here. There's literally 2 answers here. But and there's a right answer in the ideal world and the right answer in the world in which we live. So on all the computers we use, like this is your phone, this could be your laptop or your desktop at home, you're cool if you have a MacBook, all those computers are little Indian. So they store the numbers backwards. So the first byte is going to be EF. Okay, because they take the 4 bytes that make up that number, and the highest byte, the most important byte, is BA, like most people put down. So BA is the most important byte of the number, and they store that last. It's kind of weird, right? This is Little Indian. It's kind of weird, and the weirder thing is everyone, all the commonly used platforms today store numbers backwards. So the most important byte is BA, the least important byte is EF. I'm sorry. The most important byte is not BA. The most important byte is B, right? Because the first byte is B. Those are the first 8 bits. The next 8 bits are AD. The next 8 bits are BE. And the next 8 bits are EF. So EF, those last 8 bits, those are the lower part. Those will be stored first because Little Indian stores it backwards. Now, we really should be storing B first, right? Because that's the most important part. And when we write numbers, that's the first one we would write down. That's called Big Indian. It's also called network byte order. Okay, and that's also the easiest to debug. But that's not the world we live in. So our computers store EF first. Okay, so not super important for what we're going to talk about. I just need you to understand that there's different ways to store numbers. Okay, I'll just write it in the chat so that you can look at this later. Okay, so it's the Big Indian versus Little Indian question. Little Indian says store the least important bytes first. The least important, the smallest, are EF. So like when you get your first paycheck, right? You go to your first job and they're like, we're going to pay you $100,000 a year, right? Oh, Greven. Okay, but 100,000 Greven. Okay, we'll just stick with that. $100,000 a year. You're like, yay, right? But if you go to your first job and they say, we're going to pay you $100,000, $100,032. You don't really care about the 32. That's the little part. The 100,000, that's what you care about, right? The 100 part. So that's big versus small, but the 32 will be stored first. It's not because of assembly exactly. It has to do with the CPU architecture. The CPU architecture decides, the CPU decides how it's going to store the numbers. So if it's going to store the 4 bytes of an integer, it decides whether to put the smallest byte first or the largest byte first. It seems weird to put the smallest byte first. There's some nice properties that arise when we do that, which we won't go into, but that's why it's done. And it's interesting that today with the sophisticated processors we have, Little Indian has one. Okay, so that's where it is everywhere. Okay, and that includes even if you're using C, C++, and you store those bytes onto the disk, it's going to store the smallest first on the common processors we use today. All right, let me go. Oh, okay. Here's another one. So this is your test of encryption, just to get an idea of your crypto knowledge. We have the expression on the right, G to the power of A to the power of B. So you take G to the power of A and then you raise it to the power of B. That equals G to the power A times B. Okay, so this expression is the basis of one of these technologies. The first one is RSA, Revist, Shamir, I can't remember what the A stands for. The next one is, it's a public key technology. Diffie-Hellman, DH, is another public key technology. AES is for symmetric encryption, for bulk encryption. And SHA-256 is for digest or hash function, cryptographic hash function. Okay. Cool. And again, I'm not looking at the right answers. I don't care about. This is just so that when we talk, I know, what intro I should give, what kind of material I should cover before we jump into topics. Okay, so the right answer here is Diffie-Hellman. Okay, Diffie-Hellman uses public key, and this property is a key property of Diffie-Hellman. And the key is the commutativity of A times B. We can switch those around. So Diffie-Hellman has a really nice key exchange protocol. It's the one I can remember from heart. I don't have to look up anything. So it's quite nice. We use Diffie-Hellman a lot. We generally don't need to implement it because there's great libraries out there that are very efficient. Okay, so the right answer here is Diffie-Hellman. Okay, although I should mention the result, the G to the AB, is usually what we base our keys and our message authentication codes on. So the keys for AES and the keys for digest or message authentication codes based on SHA-256. All right. Okay, so oh dang. Actually, I didn't mean to. Okay, we'll come back to this. But in the meantime, just at the very end, in the meantime, I wanted to move to, sorry, I'm not as good at Zoom as I used to be. Let me move, which one I'm sharing. Okay, okay. Okay, so now we're going to talk about distributed systems. So, whoa, why does this look different? Sorry, I'm sharing the wrong thing. Oh, here we go. So we're going to talk about distributed systems now. And this is why I love distributed systems. I always liked magic. Since I was a kid, I liked reading The Lord of the Rings and Harry Potter. Like all the stories about magic, I always wanted to be magical. I thought that was so cool. Or have like superpowers in my brain, like being able to move objects or read people's mind or communicate over great distances with my mind. I always thought that was neat. Now, today, we can do that. Like, we can do magical things. I can be at school and I can know that somebody rang my doorbell at home. And then I can look at them, right? Remote present. I can look at them and I can talk to them remotely. When I'm in Ukraine, if somebody rings my doorbell, I'll be able to talk to them as if I'm inside the house, which is really cool. And that's magical. And the reason it works is because of distributed systems. So distributed systems mean any system with more than one computer. Okay? When we're, at least at our university, when we write programs in classes, especially in the lower division classes, it's always a program that runs on our computer. Okay, you write a program, I don't know, it calculates something, it prints something, it formats something, but it's always just running on our own computer. However, a distributed system is a system in which two or more computers are involved. So let's just take a very simple distributed system where we have two computers, this computer here, and this computer here. And these computers communicate with each other to provide a service, some sort of application, right? And this is how everything is built today, all the services we use. You have an app that runs on your phone. Usually that app talks to a remote server. I love Clash Royale. So it's a game you run on your phone, Clash Royale, in which you play, you have a little battle with another person, right? This Clash Royale game involves at least 3 computers, like your phone, the other person's phone, And then there's a server on the internet that's kind of, being the referee or the judge between this game, is controlling everything. So those are the interesting things that are built. Right now we're on Zoom. There's lots of computers involved in the Zoom call. There's my computer that's transmitting the information. There's the Zoom server that's like managing all the data. There's your computers that are rendering this. So this is a distributed system. Anytime we have more than one computer, we have a distributed system. Okay? So if we take a simple distributed system here, we'll have a program running on this computer. So let me just represent this little program here and this little program here. Okay, it's terrible. I'm not an artist at all. So we have these two programs running, and they need to share information. Now they share information using a network. So these are connected via network. So usually these networks are like wireless networks, Wi-Fi. Maybe they're a cable like Ethernet in our house or to the internet. Doesn't really matter how they're connected, but they're connected over a network. Now, there's a problem. It's a classic problem in distributed systems where this computer, maybe it has a linked list, right? So it has, a linked list of size 3. These nodes point to each other. And we want to take this linked list and we want to send it over to this computer here. Simple thing, right? We have a list of 3 things. It's stored as a linked list. We need to send it to the other computer. Turns out that's very, very hard. Okay? Seems very easy. It's very hard. And the problem, the reason it's hard, can start to be shown by just talking about integers, like we talked about before. So we have the number. We had, what was that? Let me use the number we had before. We had the number of bad beef. Oops, sorry. Oops. Bad beef. Okay, this gets cut up into, so we have this number, bad beef. That's the number we have. When it gets stored in memory, when it's actually put into bytes, what it really looks like is EF, BE, AD, and B. Okay, so we have an integer, and we want to send it over the network. Now, we have this problem. It's called the serialization problem. It can also be referred to as marshalling, where we need to take this number, this integer, and we need to change it to bytes. Okay? Now, why do we need to change everything to bytes to send it over the network? Does anyone know? You can put it in chat if you want to. Like if we have a 32-bit number and we want to send it to another computer, why do we have to convert that 32-bit number into bytes? Why can't we just send the number over? Okay. Okay, good. Yeah, so so the computers communicate with each other over this network link, and that network link is composed of bytes. So when we send something over the network, we're sending bytes over the network. Just like when we write things to files, we have the same problem when we write to files. So if we have this 32-bit number and we want to write it to a file, that file is composed of bytes. We need to store it as a byte. Okay? So we have this 32-bit number, we need to convert it to bytes. Now we need to decide, are we going to store it big endian or little endian, right? The CPU, our CPU has already decided. it's storing these 32-bit numbers as Little Indian in memory. We can do that same thing when we write it to a file and write it over the network, or we can choose to store it Big Indian and send the most important byte first. Oftentimes, that's what we choose to do when we send things over the network. Certainly with the historic protocols, when we send these bytes over the network, we send the most important one first. That's why Big Indian is also called network byte order. Okay, so we see the problem of sending information starts as soon as we start talking about things bigger than a byte, like an integer, which is a pretty simple thing. Now, when we talk about more complex data structures, it gets harder. So if we look at this linked list here, this linked list, it might be composed of, maybe it's a list of students and grades. So we have a name, and then we have a grade, and then we have the next pointer, right? So, this might be Ben and C plus. Oh, I think you all use numbers, right? So maybe a 3. I don't know if the 3 is good or bad. Right? And maybe the next one is Amy, and Amy has a 2. So and then we have this link between them. So how do we send that over the network? That becomes more difficult, because now it's not just about sending a number over. I mean, the grade is a number. So let's say this is an int, and this is a string, and this is some sort of reference. Whoops. Okay, so depending on the language, this might have a star in front of it, maybe it won't, right? But this is the reference to the next thing in the list. So we need to send this over the net. We need to convert this structure into bytes. And then we need to send those bytes over the network. And then, so this is going to, we're going to take these, convert it to bytes, right? These guys are going to get converted to bytes. They'll get sent over the network. And then on the other side, we're going to receive these bytes. And we're going to need to reconstruct this data structure. Okay? Do people see the problem here? This is a non-trivial thing to do. And if you have to do this continually in your code, it becomes very tedious. You end up writing a lot of code to just convert your data structures to bytes and then convert them back. So we call this to serialize your data structures and deserialize your data structures, or to marshal your data structures or unmarshal your data structures. So fortunately, there are systems for doing this automatically for you. So you have a system like Google has a system called, called protobufs. But there's many other ones. There was a Sun. There was an old. They're gone now. But there's an awesome company called Sun. They had a protocol called XDR. There's open source ones. Avro from Apache. So there's various of these libraries that will help you convert your data structures into bytes and back, to serialize and deserialize. Oh, I should mention, Java had a thing called serializable. Let me scoot this over just a little bit. Come on. Why doesn't this move? Oh no. Wait, sorry, you got it. Okay. Called serializable. And that was really cool. When Java came out with serializable, it looked like it was going to solve other problems. You just mark your data structures as serializable, and Java serializes it for you. It was cool. It didn't really take off. There were some problems with it. One of the big problems is it didn't work across languages, because that's the other thing we need to do. This program, for example, might be running Java. Oops, Java. And this program, for example, might be Python. So if this program on the left is Java, and it's sending a linked list to the right to Python, when Python deserializes those bytes into a list, it's going to look very different from the list in Java, right? It's going to use Python list. So this is the problem that these serialization libraries start to address. Okay, so this is a serialization problem. I'm going to focus on Google's solution, protobufs, not because it's the greatest solution, but it is quite popular. Okay, and there's support for almost every language. So let's look at what we can do if we have serialization. So let me draw our two systems again. Okay, so we have this linked list here on this computer here. Okay, and this is grades. Okay, so we have these grades, and what we want to do is send it to this computer over here, right? So we want to send these grades to this computer over here. Now, usually, when we send something to the other side, there's a context. There's an action that we want to take place with these grades. So, for example, we don't want to just, when we send the grades to the other side, we want the other side to do something with it. For example, maybe we want to register the grades. So we want to register, and then we take these grades, and this will add it into some sort of grade database. Okay, so that's why we're sending this linked list over to the other side, because we want to register the grades. So once we have serialization, we realize we can do something better. Because when we talk to another computer, we don't just want to send data, we also want to cause some action to occur. So for that, we have something called RPC, remote procedure calls. We see RPC happen with REST. I'm sure some of you have probably used REST. Let me just write that. So REST is a form of RPC. Okay, it has some action, some data associated with it. Oftentimes, REST is used with JSON. Okay, so JSON is a way to serialize data. It's a way to take a list or structure and put it in a format that you can send over the network. That's JSON. Has anybody, what's one of the challenges of using JSON? Is there any kind of data that is hard to send if you're using JSON? For example, if you're sending strings and integers and structures with JSON, it works perfectly. Like you have this JSON format. Ah, yes, this is the problem. If you want to send images, videos, anything that are bytes, it's a problem. And Alexi, points out the solution. We use base 64 encoding. What does base 64 encoding do?
It encodes images to string to.
Exactly. It encodes images to a string, or it encodes more generally binary data into a string. And so what does the 64 come from? Does anybody know? Or do you know what the 64 reference is?
Amount of ASCII characters that can be used.
That's right.
encoding.
Yeah. It's the number of digits that we have. So you know, if we take let me just do this really quick. I don't want to get too distracted here. But if we take so if we have these bytes, let me so if we have these bytes, we have 4 bytes. So if we have these 4 bytes and we want to send them over the network, we can't just send and it's binary. We can't just send it in JSON because some of those bytes will be curly brackets. Some of them will be, quotes, and those bytes are gonna mess us up, right? That's not gonna work. So we need to encode them. We need to take those bytes and represent them with something smaller. So one thing we can do that was simple was called nibble encoding. And nibble encoding takes a byte and cuts it in half to a nibble. So you take each byte, you slice it in half. Now these are 4 bytes or 4 bits. And then this 4-bit you can just convert to hex. So that means for every 4 bytes, you generate 8 bytes of hex. And that's great. You can send those hex strings over the network and everything works great. The problem is you've just doubled the amount of space you're going to take. So you can look and say, okay, well, hex is base 16. Okay, what if we wanted to, instead of do 4 bytes, we do 5 bytes? Well, 5 bytes would be instead of 4 bits, we do 5 bits. 5 bits is base 32. So where this is A to F, or I'm sorry, this is 0 to 9, A to F, we can now do 0 to 9, A to F plus 15. I don't know. I'm going to guess O. I don't know. But we can use a bigger range of numbers. Okay? So what if we take that to the extreme? Well, if we use 0 to 9 and A to Z and lowercase a to lowercase z, this gets us, this is going to be 26 plus 26, which is 42, plus 10, this is going to be 32 possibility. Okay, Bill, possibility. Let me just say it possible. So that's 32 possible digits we can represent. So if we can get to, I'm sorry, not 32, 62. So if we can get to 64, that will give us another power of 2, and then we can encode 6 bits at a time. And so we do that by just adding 2, plus and slash. Okay, so we add 2 more digits. Now we have 64 possibilities, and we can represent a base 64 number. So that's where base 64 comes from. Okay, so this allows us to convert to string. So that's, and that works well. I mean, it's very common. It does expand more. It does require some processing. The nice thing about protobuf is it actually does binary encodings, so we don't have to do this expansion, and we can handle binary data much better. So, but what I'm about to say works with REST as well as RPC and gRPC. So specifically, I'm going to talk about gRPC. Okay, so what we really want to do is send this data over, these grades over, and we want to say register, and we want to pass these grades. Okay, now when we do this, we need a way to not only take our grades, convert them to bytes and send them over, we also need a way to specify to this side here that we want to do the action register. Because there will probably be other other actions, such as what is Amy's grade, right? To query grade, to list grades. So there's probably a multitude of actions. So in order to make this work across different languages and specify what we're going to do, we use something called an IDL, Interface Description Language. And what a lot of these frameworks do is you specify how you're going to communicate, the structures you're going to use, and the actions you're going to perform. You specify that in a file. We'll look at an example of that file in just a second. And then you have a compiler that will take that file and generate code for whatever language you want. If you want Java, it will generate Java code. If you want Python, it will generate Python code. If you want C#, it will generate C# code. And it will generate code that will take these grades and convert them to bytes. That's one thing it'll do. It'll also generate code that will package up data along with an action that it can send to the remote side to get processed over there. And it will generate a stub and a server implementation. So what this stub does, when you want to communicate with this remote process over here, you need a way to tell it something, to do something. So when this was first, when people started thinking about how to do this communication early on, they realized there's a very natural way we have in programming, when we write a program, to talk to a library. So you've all used libraries. You write your code and you want to perform a regular expression on a library. You use on some string. You use the regular expression library. You want to connect to a remote service, like you want to pull something from a URL. You use a URL library or an HTTP library, and you specify the URL. You call this connect function, and it will return the data. So we have this notion of calling library functions to get service, right? Well, what if we extended that? So instead of having a local function, we call a function that looks like it's local, but it's actually remote. Thus, the remote procedure call, like the remote function call. So what we do, well, what the compiler does, is it creates a stub object. And this stub object will have a register function. So when your code calls this register function, it takes the register function, and this register function will have a grades that get passed in. So this generated code will take these grades, it will serialize them, and then it will package them up with the action register. And it will send this package over to this machine here. When this machine here gets it, it will unpackage the grades, and it will look and say, oh, we want to call register. And it will invoke a register method, a register grades method, whoops, oh no, sorry. A register grades method here, it will invoke it, and then it will return whatever gets returned, it will repackage up and it will send back to the other side, and this function will return. Okay, all very magical, sounds very cool. It is very nice to use initially. When you use gRPC, you can write code that does things remotely pretty quickly. However, there's a couple of problems. One problem is the API, the way you do this is a little bit clunky, as you'll see. You'll see in just a second. Although Python makes it look pretty good, but in other languages, it's kind of clunky. The other problem is we have a classic distributed systems problem where when problems happen, when failures happen, it's really hard to understand what is going on. So for example, if we call this stub function here, so we call this stub function and we go to register the grades, and then we never get a response. We call register grades, we never get a response. What does that mean? Well, it probably means that the machine failed. It could also mean that there was a network problem and we just lost the response. So, okay, so if there was a failure, if there was a machine failure, or if there was a network failure, did it fail before the grades were registered? Or did it fail after the grades were registered? In other words, did the request get lost, or did the response get lost? So that's a problem. Now in this case, we could just retry the register. But if you're sending money, for example, if you're doing a bank transaction and you say, send $100 to Joe. So you call that, and the bank responds saying, communication failure, right? Actually, okay, so you never get a response from the bank. You set this up, and then you get a communication failure from your library. Okay, so the communication failed. Does that mean that the bank received the request to transfer $100 to Joe and the response got lost, or did the request get lost? So if we say, well, I just want to send it again to make sure, you might end up sending $200 to Joe. If you don't send it again, Joe might not get the response. Okay, so we can talk a little bit more about this decidability problem. But since we're running low on time, let me just point out something for you to look at. I have an example of using gRPC. It's in, sorry. I put it on GitHub. Actually, let me just copy this URL for you. Okay, this is something you can look at. I have a server running on the internet, a gRPC server. You can play around with it. This is an example of an idea. So we have a service, and this is a translation service. Okay, gRPC service. Okay, and the service it implements is to translate. So you can send a message, a translation message, and the first parameter is translate to, which is the language you want to translate to, and the message. The assumption is going to be it's in English, right? So you send an English message, you say what language you want to translate to, and it responds with the translated message, or an error if it can't translate the message. Okay, so this is a very, very simple gRPC server, but we can kind of see this is where serialization gets involved. We have these two structures that come back. One is an example of a simple structure. The other one is an example of like a union type structure. Okay, and then we have a call that we want to make. So in here, in this code, you can look, here's an example of a gRPC server that, that I've implemented. So this is the gRPC server. This is the implementation of translate. You can already see it's not as cool as it sounds. Okay, you get a request, and then you get this object that you feed a response to. Okay, so, and the server, since I'm American, and Americans, we don't speak other languages, we invented this language called Pig Latin. You can look it up. It allows us to sound bilingual without actually learning anything. So the only translation that we can do is Pig Latin. So if we don't get a request to translate to Pig Latin, we send an error back. Otherwise, we translate it to Pig Latin. So yeah, so if it's not Pig Latin, we send this error. So this is, you can kind of look at this, you can play with this. There is a server running that you can connect to. You can look at the Python code for example of how to use it. So I have this, this server running on this port here. And in this little test client, I connect to there, and this responds with a channel, and then right here we make this stub. So this is the call to make the stub. And once we have the stub, we can call the translate function on the stub. And here we see the two requests. So I encourage you to play with it, try it in other languages, just get a feel for gRPC. And then next time we can talk more about gRPC, a little bit more of the problems, and we can talk about how we can start securing it. Okay. I do have, let me go back. There's one other thing I would like you. Yes. Okay, if you could answer this question, just to give me a hint, so in the future, when we talk, I have an idea about how much is review and how much is new. So if you can kind of like, yeah, if everything is new, or so yeah, if everything is new, go to the right. And if you kind of knew everything before, go more to the left. Okay, so this is just so I can kind of adjust. Are there any questions? I know we're out of time, but are there any questions about what we talked about today? Oh, okay, why do we need to generate? Oh, yes, that is a good question. So why don't we just generate binary code? Yeah, that's a great question. So in theory, we could. Although we would have to generate binary code for each different language, not just each different language, potentially each different version. Like sometimes you have different libraries, even with C++, you might have different libraries that you're using. And so depending on the version of the library, you might need to generate a little bit different binary. And also, we would have to generate for each language, because the binary for Java, which would be a class file, is much different than the binary, which for C++, which would be a library of some sort. And Python, yeah, it's not going to be really binary. You can kind of do compiled Python, but that's very different. So I think the reason we don't go to binary code is more of a matter of tooling than a matter of technical problem. It's just very practical to separate your compile tools, the things you use to generate binaries, from your tools to compile an IDL into a specific language. So that's why you get the source code. Also, from a very practical matter, having the source code for this like glue, this intermediate, this intermediate glue really helps with debugging. Oh, yes, yeah, for gRPC, there actually is a good site. Let me pull it up. That has training and everything actually. So yeah, I'm glad you asked. So if you go to that site, grpc.io, it has documentations, I think it has videos on there, it has training, and it also has language-specific tutorials and how to use gRPC with different languages. So I use it. It's a good site. Wait, let's see. Oh, hold on. So the meeting is being recorded. I don't know where it will go. I think Yuri can answer that question. Yeah, so it is being recorded. Yeah, that is not, you're right. It's a classic. Yeah, yeah, it's very true. Yeah, there are. We can talk about this too. There is this result. It's called the impossibility result, which is called FLP. There's this very interesting result that they came up with, which was if you have a distributed system, so you have multiple processes and they're acting independent, but they're connected with a network, which is, I mean, that's today, right? They're connected with a network, but they don't have synchronized clocks, which again is today, right? All our computers, their clocks are a little bit up. So you don't have synchronized clocks, and the messages might be delayed or out of order. Like when you send messages, they might be delayed or they might come out of order, but no messages are lost, which is even better than we have today. So if you have those guarantees and one process can fail, right? There can be delays in messages and one of the processes can fail. So you might have 100 processes. You can't make, you aren't guaranteed to be able to make the simplest decision. So let's say you have 100 processes, they're connected on the network, and they just need to decide yes or no. That's it. But they all have to decide the same thing. So all of those processes have to decide yes, or all of them have to decide no. They start out with different states, but in the end, they need to come up with the same answer. If there can be a failure and there's delays, you can't always do it. There will always be a case. There will always be a way in which processes can't decide, no matter how many messages you send or how long it takes. So it's a really interesting impossibility result. Now it turns out in practice, we can make that case where we can't decide extremely improbable. But in a distributed system, we do need to recognize that there will always be problems. There's always a small chance for a problem. We just need to make it small enough. Which sounds a little scary, but even on the system, like the memory we use, it's, you know, it's not perfect. So there can be some memory corruption occasionally. On our hard drives, on the storage, like everywhere, we have these error detection, error correction codes. There's always a chance, that very small probability that the errors will seep through. So we don't live in a perfect world, and FLP kind of shows that. All right. Yeah, exactly. The compilers, this is why gRPC works the way it does. It works hand in hand with the compiler for the language. So gRPC will take an IDL, it will convert it, it will generate some code in a given language, the target language. And then that target language compiler will turn it into binary code. So it's kind of a two-step process. Ah, yes, that's a great question. What are the advantages of building a protocol on top of HTTP instead of building on top of pure TCP? Right. So it's really, so theoretically, TCP is much more advantageous. It's much more efficient. Like you don't have the overhead of HTTP. HTTP headers have some, they use a lot of strings. It's kind of inefficient. So TCP in theory is much more advantageous. However, the internet infrastructure, like the world in which we live, is very tuned to HTTP. So your routers, your firewalls, they know about HTTP. It presents higher level abstraction, so you can do some firewall filtering based on HTTP. So the advantage is really more of a practical advantage than a theoretical advantage. There's just a lot of infrastructure that's in place to handle HTTP nicely. We have HTTP proxies. There's really nice HTTP proxies out there that we can build on top of instead of TCP. Okay. I mean, HTTP comes with security already built in if you use HTTPS. So it's more of a practical advantage based on infrastructure that is already exists in the network than any other advantage. Because if we're using gRPC, we use very little. HTTP itself doesn't really give us very much.
I have a question.
Sure.
How often do we use gRPC in real projects? Like, is it highly requested skill or it's like for certain people?
Yeah, that's a good question. So it really depends. It depends. It's kind of like asking what language is most requested. It depends what you're doing and where you are. If you're going into data science or machine learning, Python is what you need, right? Unless you're doing machine learning infrastructure, and then you're probably doing C++ or maybe Java, right? So it kind of depends. A lot of like public HTTP or public RPC type services use REST, which does not use gRPC. That uses HTTP and JSON. But if you're going into a lot of internal systems do use gRPC. A lot of Google services use gRPC. It just kind of depends where you are. There's other, like if you go to Facebook, you're going to use Thrift. Thrift is I'm sorry, they're called Meta now. If you go to Meta, they use Thrift for their internal RPC calls, it's very similar to our gRPC, but different. Some of the other big companies have their own RPCs as well.
Okay, thanks so much.
Sure. Yeah. Wait, let's see. Yeah, I guess, so you bring up HTTP 2, and you should also, we should also mention QUIC, QUIC. So that's another reason built on top of HTTP is you could, as things evolve with HTTP to make it more efficient, you do get that benefit. So if you're building gRPC on top of HTTP, then you can move to QUIC kind of transparently. Another server require the same function. Right. Oh, that's a great question. Yeah, so generally there is this more general question of what happens if you call a server and that server doesn't have the function, or it has a different version of the function. So if it doesn't have the function, it will return an error. And this is another problem with remote procedure calls. They try and look like local procedure calls, but in a local procedure call, you would never get the error that function is not implemented, right? Your compiler would have figured that out before your code even ran. But when we do remote procedure calls, you can make a remote procedure call and the return code could be that function isn't present. You also might make a remote procedure call and you can pass a request and you can pass some data. And then the answer you get back might have a version of the response that is a later version or an older version than you're expecting. So different RPCs and different serialization libraries have a mechanism for this. The good ones do all address this problem though. Some of them address it in different ways. But you do need a way to say, look, I just sent grades, and the server will get these grades, and the server will say, oh, let's see, I see a name, I see an age, but there was supposed to be the name of the professor. There's no name of professor. So it will see that there's no name of professor there, and it will need to make a decision about what to do. So there is this versioning problem that we need. Yes. Yeah. So yeah, that's one thing you need to handle with gRPC, that you need to realize is that with gRPC, there's this versioning problem that we have to deal with as well. So as you communicate with different servers, they might have different responses. Now there are practices, there's best practices with using gRPC and with using RPC in general that you can do to deal with this. It's a problem that comes up with JSON too. If you send a JSON request to a remote server or you get JSON back from a remote server, you need to be prepared to like not find something that you're looking for, or to find extra data that maybe you'll just ignore, right? That's usually the easiest. So usually the easiest way to deal with this is ignore what you're not expecting and have defaults for what you expect but don't see. But it's not a trivial problem. The scheme is required to see. Oh, wait, let's see. Yes. So yeah, that's a great question about schemas. So when you send requests to the other side, how does the other side know what to expect? Like when it gets this serialized data, how is it supposed to interpret it? The general answer is you need a schema to interpret it. But there are different answers to that. gRPC doesn't really have a schema. It has elements of a schema. Actually, so if you look at JSON, like raw JSON does not have a schema. You can look at the raw JSON, you can say, oh, look, that value is a string, or that value is a structure, or that value is an integer or an array. But it doesn't really have schemas. Now they've added JSON schemas on so that you can get some schemas, and so gRPC is like that. It has some basic information about data types and structures that it's sending over, but it doesn't actually send the schema to the other side. Other RPCs like Avro, for example, does. It actually sends a schema to the other side and says, hey, look, before I send you anything, this is what the data is going to look like. And then the other side will need to look and say, okay, well, this is what I expect the data to look like. And it will need to do some schema matching. So it depends on the different RPCs about how the schema is learned and how the data structure is learned. Yes, you're right. In general, in order to process, in order for the two sides to be able to process data from each other, they need to have protofiles that are similar. So they need to have some version of the same protofile. There are ways that you can actually do it without. I mean, you can use reflection to kind of interpret the data the way you will, and then try and figure out what to do. But generally, for things to work and to actually do things in a reasonable way, both sides have to have a protofile that is that is the same. They might be different versions, but they need to be the same protofile. No, actually, that is really sad. With gRPC, there's not an endpoint to get the protofile. It would be really cool. Some of the other RPCs, you can. When you can contact the other side and you can get a schema. Another big RPC that was going to take over the world was SOAP. That was based on XML, and a lot of those had ways to get schema. That one was very complicated. Yeah, so it just depends. No, I would not consider, yeah, WSDL is the thing. I agree. I don't think it's a security concern to not exchange the schema, because even without the schema, there is information in the encoded data that's sent to the other side where you can kind of figure out how things are working. It takes a lot more work to do, but not having the schema doesn't, I would say is not a security issue at all. If you have enough data, you can kind of figure out the structure based on just reflection. There's some basic structure there that you can pull all the data out. And then if you have enough data, you can guess what each of the fields are. I think it's more of a simplification thing to not exchange schemas. Ooh, yeah. Oh, GraphQL. Yeah, GraphQL is completely different. GraphQL is more like SQL, like a database. GraphQL kind of takes a different approach. It says, well, okay, rather than communicating with a remote server using a function paradigm, we communicate with a remote server by making the remote server look like a database. So yeah, GraphQL is completely different. It's pretty cool. I like GraphQL as well, but it's quite a bit different. Yeah, so when you do so I encourage you about converting the function. I encourage you to try out the gRPC tools. You can look at the project I put up and generate some stub code, and I think that will answer your question about conversion. But to answer it quickly, yeah, the whole thing is converted. Yeah, the function is generated from scratch based on the compiler, and all the structures are generated from scratch. Protobuf is space efficient. However, when you get a protobuf blob, so when you get this chunk of protobuf data, that data has structure in it. So all of the fields have a marker. So when the data is encoded, the first couple of bytes tell you the structure that follows. So it will say, oh, this is a structure, the size is this big, and it has this version number. And it does that kind of recursively. So you can, it's kind of like JSON. You can actually take a protobuf binary and generate a root, what could look like JSON if you wanted to, from just raw protobuf data. But it is efficient. I mean, everything's binary encoded. It gets around the problem of unexpected strings by encoding lengths. So it will say, okay, these bytes, they're there's 4K of bytes that follow this byte. And then those 4K bytes can be anything. So that's why it's efficient. Oh, it's almost like a version number and a bunch of bytes smashed together. It's almost that. It's just that those bunch of bytes, if they're encoding a structure, there will be a little bit of structure inside of there too. So it is a little bit more than a bunch of bytes. Yeah, the reason they don't rely completely on the schema for pulling it apart is because of this versioning problem. So the bytes, the protobuf bytes that you get back might have a different schema than the one you generated your code with. So when those bytes come back, it needs to be able to look at the fields and see, oh, this field was unexpected. I'm going to ignore this, right? So that's why there's a little bit more encoding inside of those bytes than you would expect, so that it can deal with this versioning. Because the version difference might not be on the outer structure. There might be an inner structure that has a little bit different version. And so that's why you need to have this structural representation all the way down. Okay. Oh, yes, there are some very good ones. Actually, there is a book. I'll put up the book the next lecture. There's a very good book on this. I use it it's an O'Reilly book. I use it for my classes. But there are many alternatives to gRPC, and they're robust. Some of them take different approaches, but they're industry standard and they're efficient. Sometimes they're more efficient in certain circumstances than gRPC, sometimes less. But yeah, there's a lot of implementations of gRPC out there. The reason I bring up gRPC in particular is because as far as open source goes, it's the one that is most supported in open source. It has the most language bindings, so you can use any language. But it's not, I wouldn't say it's the only robust one or the only commonly used one. There are different ones out there. And certainly within large tech companies, a lot of them do have their own remote procedure calls as well. The thing that happens though is inside of large tech companies, like for example, Thrift inside of Meta, their language bindings are for like Python, Rust, C++, and Java, because that's what they use, right? They don't really care about Haskell because they don't use Haskell. So, okay, they use it in some places, but so it's not why the languages that aren't used internally, they just don't care about. Whereas gRPC, it just took off in open source. And so it's widely supported across different languages. But it's definitely not the only one. Okay. All right. Well, yeah, so it's Apache Thrift. However, I think Facebook stopped, or Meta stopped updating Apache Thrift. I could be wrong. Maybe that changed. But for a while there, they weren't updating Apache Thrift with their own internal stuff. I'm not sure how they diverged. But Apache Thrift did start with Meta's Thrift. So yeah, I'm just not sure how up to date that is. The other popular, I shouldn't say popular, but the other robust one is Avro, Apache Avro. Let me just write it. The Apache Abro is another very good RPC framework. Facebook one, the one they use internally, I don't think they have open sourced it. I mean, they did open source it, but the latest version I don't think is open source. As far as I know, I haven't kept track of it. So. All right. Well, thanks for the questions, everyone. It was great talking to you, and I hope I can meet some of you next week. So, and thanks, Yuri.
Ben, thanks a lot for interesting and useful lectures. We continue on the next week. Announcements for students will be in our site, in the Telegram group, or on other announcement. Please join us on the next week, and after we have several offline meetings in our university, and this announcement will be in our site and our Telegram group. Ben, thank you a lot. Thank you. Very interesting.
Great. Thank you.
Thank you,
right.
Ben, for very meaningful lecture.
Great. Well, thanks for letting me do this. It's very great to engage with you all.
Thank you a lot for your lecture. It was very enjoyable, and
Great.
I learned something new. Have a nice day and goodbye.
Great. Thank you. Дякую.